All right, how's it going, guys?
Good.
Good stuff. So this is 370 office hours for project 1A. We can also go into project 1S and stuff, but this will mostly focus on 1A. We're here for about an hour and a half. My name's Max. I'll be leading this today. So before we get started, does anyone have any burning questions about the project that can help everyone else out here? All right, cool. So what I want to do today, and we can always change it up if you guys want to, we're going to mostly focus on how do we translate the spec into machine code manually. And hopefully that helps you guys understand the project and what we need to do for the actual project itself. Everyone cool with that? All right, cool. So a couple of things I'll highlight first. We're actually go ahead and translating it, and that is our first pass. So whenever we're working with an assembly file like this, we need to know where our labels exist. So a label is defined on this left-hand side right here, and we know that because a label's on the left-hand side, and that tells us what line number it occurs at. So assuming that the first line is line 0, that means start will map to line 2, done will map to line 6, 5 to 7, second one to 8, and st adder to 9. So what we should be doing in our first pass is basically going through our assembly file, and if the label exists, we're going to go ahead and put it inside a container. Now in C, we don't have any options for containers because we only have arrays. So we can go ahead and make a 2D char array for this to hold a label at a given line. So essentially in that case, our index will be our line number, and then the value of that will either be an empty label, meaning there's no label present at that line, or it'll be the label itself. In discussion, we talked about the string copy function. This basically takes this label right here, and you can copy it to somewhere inside your array. Any questions about that? All right, cool. Yeah, go ahead.
So you have to initialize this size of the array responding, right?
Yep.
So can you just make it size 100 and
Yeah, sure. So we actually give you the max line limit for an assembly file. And since we can only have one label per line, that means your array could be at most max line limit. So you can make your array that size if you want.
Okay, so that gives you certain indices without anything in it.
Yeah, and that's totally fine, right? Like for example, on line 0, if we say what labels at line 0, we should have nothing there, right? It should be an empty string. Yeah, cool. And then also labels can only be 7 characters long. So if you want to go ahead and specify that as well in your array, you can specify it as being like, oh, the maximum line length by 7. And I'll go ahead and give you the proper size for your label container. And then a couple of things for error checking for this. What you should first look out for is a label defined twice? So for example, I write startup here. If I'm looking at this line right here, BEQ 00 start, that means I'm going to go ahead and set my PC to wherever start's at. But since start is defined twice here, we can't resolve that, right? Because start is defined in 2 different places. So in that case, we go ahead and exit 1 and say there's an error. So whenever you're processing these labels, before you put them inside your map, just go ahead and make sure that doesn't already exist. And then one other error is what if start isn't here either? So if I'm at the BEQ line, right, I'm going to break if this register's value is equal to this register's value, I'll go to start. But since start isn't defined over here, we don't have behavior. So in that case, we're going to exit 1 as well. So those are the 2 main errors: is duplicate labels and no labels at all. It's totally fine, by the way. So let me put the start back real quick. How about this? We have st adder right here, but st adder is never referenced over here. Is that fine? Anyone know? Yes or no? Who thinks yes? Yeah, it's fine, right? Because it doesn't matter if we don't reference it, right? It's defined, but it's never referenced. That's totally fine. So you never have to check to say, oh, is st adder referenced in one of the load words, store words, or BEQs? Don't worry about that. So that's about it for the first pass. Do you have any questions about that? With error checking and how you should store the arrays or your labels inside an array? Yeah, go ahead.
Labels you register.
Oh, sorry, what was that?
You write start in the.
Sorry, I can't hear you. Can you speak up?
You write the start in the third line. Third column.
Third line?
Third column.
Right here?
Register.
Register? Right here?
You use a label to label the register.
In the load word instruction right here?
Can
Yeah, you can go up. Yeah, come on. It's fine. Here you go.
you write here.
Sorry, what's your question?
you write the command. You don't write one, right?
Oh yeah, you can't do that.
Can't.
You can't, no. So the way load word works, and this is actually really important, so glad you brought this up.
And will the register be?
Yeah, I can explain load word again if you want me to. So the important thing, so let's go over some assembly stuff real quick so we're all on the same page here. We'll go over how load word works. So load word 015, what this means is we're going to load a value in memory into register 1. So how do we actually figure out what we're going to add to memory? What we're going to do first is go ahead and figure out what the value inside this register is right here. This is register A, right? So does anyone know what the value of register 0 is? It's always going to be 0. That's the idea behind reg 0. You can't change the value, but you shouldn't. And it's going to be 0 right here. And then when you go ahead and figure out what line number 5 is on. So 5 is defined down here on, I believe, like line 7. So what we do is we go ahead and load the value of 7, the value at line 7 plus 0, so line 7, which is 5. We'll go ahead and put the value 5 into register 1. This argument here and here have to both be registers. The offset can be a number or it can be a label. That make sense?
So this is all done on the first pass.
Yep. No, this would be the second pass. The first pass is just figuring out where's 5 defined. So our entire goal here is like we want to think of this program as basically this being a number. So this number 5 is really 7, right? Because 5 is defined in line 7 down here. We don't know that in our first pass though, right? We have to figure out what number is 5 really. And that's the line number it occurs at.
So that would be like the seventh position in the array. That's how we would know.
Yep, exactly. So you iterate through your array, and it's like, let's say you're iterating like by I equals 0, I is less than your maximum size. And I7, you compare the strings, and 5 is 5. Then you know your label occurs on line 7. You can go ahead and then that's your offset. For the simulator, so this is part, was it 1S or something like that? Yeah, simulator. What you want to do is go ahead and take the value inside this register and add it with this, and that'll tell you where to grab your value from the memory. For 1A, it's not important. For 1A, all you have to know is how do you figure out what the address of 5 is. And your first pass, you put inside your label map, you're all good.
So you mean that if we have undefined labels and duplicated labels, it won't appear in the project, or we should exit to 1.
You should exit 1, yeah. So if your labels, again, let's say you have start twice here, you'd exit 1, right? Because we need to know where to start defined. And if start's defined in different places, we can't have that. Similarly, if we have start defined nowhere, and we have to branch to start, we can't have that either, because we need to know where start's at, right? What you should think about is we're replacing these labels with a number. And we find the number through looking for a label map. If I can't find start, I'll have a number, right? That's gonna be an issue. Yeah, go ahead.
So for that error checking, should that be in the second pass then?
So your first pass should be checking for duplicate labels.
But what about the
Oh yeah, like the undefined one, second pass, yeah. Your first pass, all you're doing is defining where your labels are at and you're resolving symbolic addresses, so you call it. Yeah, go ahead.
Wait, so in the first pass, where like the left column is,
Yep.
do you like calculate the offset value on the right side? Or like
So-
changing it to a number?
Mhm.
Do you do that?
Yeah, so your first pass, again, all you're doing is figuring out what line to start at, what line is done at, what line is 5 at. That's all you're doing in the first pass. These arguments right here, your opcode, reg A, reg B, offset, or best reg, don't worry about that in your first pass.
Okay, would you also put like where NGL is,
The what?
like below 5, like those ones?
Oh, yeah, you should put every label in there. So all your fill statements, yeah. Yeah, go ahead.
So on the first pass, you don't have to verify that it's not referencing any undefined labels. That's on the second pass.
Yeah, exactly. You should, in your first pass, you should only be worried about everything over here. Everything over here is all second pass stuff. Does it make sense why we do that?
Yeah.
All right, cool. Again, it's because we want to figure out how do we resolve 5 and start. We need to know a number for these two things. What line number do these occur on? Yeah, go ahead.
Is there any purpose of fill specific? Are we gonna have to implement anything for that?
For fill? No.
It's just solely kind of a placeholder. So
Yeah, so the way fill works is you basically take the value, the literal here, so 5, -1, and then for start, you would just fill it with the value where it starts at. So this would be a 2. And that becomes useful in your simulator whenever, let's say, for example, you want to load word 015, you'd go to line 5 and you would just set your offset to be this value right here. So project 1A and 1S play off each other because 1S sort of uses 1A. So 1S uses machine code and 1A uses assembly to machine code. So they kind of go hand in hand. So you have to complete 1A before you do 1S. And then 1M is like its own thing. Yeah, any questions about the first pass? Yeah, go ahead.
I just want to make sure I'm getting this correctly. So everything on that side is a label.
Yep.
And then the LW, that's like the opcode.
Opcode, yep.
And then reg A, reg B, and then offset, right?
Yeah, so it depends. You're almost right. So it's depending upon the instruction. So this is reg A. This is our destination register. This is our offset. For add, this is reg A, reg B, destination register. So the HI doing semantics. So if you go to the spec page, you'll see that like certain types of instructions have different semantics. And then there are some opcodes like pull to do that have no arguments, and then JAL-R has 2, and then BEQ only has 2 register values, and then either a number or a label. Hey, go ahead.
So when we have the number 7 stored in there, that means go to line 7, right? Not go down 7 lines.
So do you mean for load word or do you mean for
Yeah.
BEQ? Yeah, for load word, what it's saying here is we're going to load the value in memory that's located at line 7.
Yeah.
I get 7 because I do 5's at line 7 plus the value register 0, and 0 plus 7 is 7. But again, that's for the simulator. For the assembler, all you have to do is translate this 5 to a 7.
Okay.
Hey, go ahead.
Wait, I thought that to like calculate that rather than the label, I thought it was like the address that the label's at, so
Mhm.
at least 7 is like equal to the address that like the line is at.
Oh, PC plus 1, that thing.
the offset.
Yeah, I'm talking about the PC plus 1. That's for
So
BEQ.
wouldn't it be 6? Oh, that's only for BEQ.
So BEQ is a bit different. So we'll talk about that real quick. So load word and store word, this value right here, the offset, is just what line is it at. BEQ is different. BEQ changes where our PC is at. So remember, our PCs are line counter, so PC 0, PC's 1, we execute code 1 line at a time. For BEQ, if you look at this program, what's happening here is we're basically doing a full loop here. So BEQ 0, 0, start. Does anyone know what that means? Yeah, go ahead.
If 0 equals 0, go to start.
Yep, exactly. And that's always true, right?
Yeah.
Cool. That means our PC, let's say our PC is at this line right here, program counter. It'll say, is the value inside register 0 equal to the value of register 0? It is. So in that case, we're going to go ahead and set our PC equal to start. Notice here that our PC is 0, 1, 2, it's 4, right?
Yeah.
But our PC needs to become 2. So we're actually going backwards in our program. So that's where it comes into play. We need to know what's our current PC address. So 4. We want to go back 2 spaces. That's for the simulator, but it's also for what this offset is right here. What is start? How far does it go back in our code so that our PC points to start? And the answer is we actually go back 3 spaces, not 2. The reason being is because after each instruction we execute, we always increment our PC, right? So in our code, what actually happens is we're going to go ahead and let's say, for example, we're at line 4, we want to go to line 2. If we go back 3 spaces, our PC is right here. We don't execute this line and we increment our PC once, and now we're back at start. Does that answer your question? All right, awesome. So the big difference here, guys, is load word and store word both use the actual address of the label, the number, whereas because it's not relative to your PC, right? This address is relative to your entire program, so it doesn't matter where you are in your program. Well, if I said load word 125, right? And I change this to a 0. We can agree that register 1 is going to become the value 5, and register 2 is going to become the value 5. Notice how I'm referencing 5 for both lines, but this is at PC plus 0, this is at PC plus 1, and we have the exact same result. That's because the value of PC doesn't impact what we put inside the register here. For BEQ, the value of PC is important. That tells us where we're at right now and where we have to go. Does that difference make sense to you guys? Okay, go ahead.
So you can have like the same label on the right hand side.
Yeah, you can have duplicates. That's totally fine. Duplicates only matter on the left-hand side. On the right-hand side, that does matter. Or does not matter, sorry. Over here, duplicates, no. Duplicates, totally fine here. For the right-hand side, the error checking is, does 5 exist? Does start exist? And I believe this was a 1 right here, right? Is someone correct me on that?
Yes.
Cool. All right. Question?
The program counter implementation isn't really relevant for 1A, is it? That's not for 1S.
It's kind of relevant just for resolving this right here for start. But besides that, all you have to really worry about is like how many iterations your while loop has gone through. You have a
Okay.
counter, right? Every time you go through an iteration of the while loop increment it, that tells you what line you're at, and then you know where it starts to find, right? Because you can label math and stuff like that.
Yeah.
And then after that, it's just basic addition.
Okay.
That makes sense? And then for a simulator, it's going to be a bit more robust because you're basically going off of, oh, I guess at my PC to be a certain address, and I'll execute those instructions and simulate what's happening there. For 1A, all we care about is where's start relative to this line right here for a PC.
If something added after now or will be also
For the simulator or for the assembler?
for example.
For the assembler, you still want to assemble all these opcodes, right?
But these things are irrelevant with no and fork because they only have the output files without this register.
Mhm.
You don't have to register there. So
Yeah.
if something added after, we want to put zeros after the node and the code or throughput.
So are you saying when we assemble the noob and halt opcode, since there's no registers, do we have to do anything besides the number for the opcode?
Yes, I mean if something was added after node and halt.
Oh, like a 1 here?
Yes.
Yeah, you ignore that. It's a comment at that point.
So I don't need to write one. I just write a zero.
Yeah. So that's a good question. So if you're assembling noob or halt, since they have no arguments to them, right? Noob and halt means stop, noob means do nothing, no op, or do you want to call it? In that case, if you have anything over here, like any like comments or registers, you ignore them. For assembling, it's super basic. All you have to do is get the opcode number. So I think halt is like 7, so 111. And then you would just bit shift it over 22 times. And that's your line right here. Because that's where the if you look at the spec, the opcode is going to be in positions 24 to 22. And so if I know that my opcode is 111, like this, my handwriting's terrible, sorry. You do this 22 times, you have like 111 bunch of zeros going into it. And that's your answer. For a noob and halt, at least. For the other 6 opcodes, it's a bit trickier because you have these obviously you have these registers and these labels and stuff. But noob and halt, they're pretty easy to do. Does that answer your question? Yeah, awesome. All right, cool. So any other questions about the first pass? Yeah, go ahead.
Field both must be associated with the label.
What opcode should be associated with label?
Field must be associated.
Oh, what fields? Okay. Yeah, so in load word, the only field that can be associated with label is
No. I
He's
mean,
talking Phil.
oh, fill.
field
Oh, you mean like right here?
Each field must be associated with a label. If you.
Oh, no, you don't have to do that. That's totally, you don't have to do that. Here's a good example why. It's a good question though. Let's say I have an array in memory and my array is 1, 2, 3. If I have a base address for my array, let's say I have something called ARR for an array, I'll do a dot fill with a 1. I can do dot fill 2, dot fill with a 3. There's no labels here, right? That's totally fine though, because what are so cool about arrays? They're sequential in memory. We use pointers for that, right? So if I go ahead and I load the value of ARR into some register, right? And then I go ahead and then load the value 1 into register. So let's say I have load word 0, 1 ARR. What's happening here? What I'm doing is I'm loading in the value of register 0's value, which is 0, plus the my number of array. So I put a 1 inside register 1. Let's say I want to access the first element of the array, which is 2 here. If I go ahead and put the value 1 into register 1, what's then happening is I go ahead and I say array plus the value inside register 1, which we'll say is 1 in this case. So array's address is right here. I add 1 to it. I then put 2 inside this. I can then add 1 again and go to this register right here, or this memory, sorry, right here. I put a 3 in at register 1. So that's why I don't need labels for every single fill statement. Does that help you? All right, awesome. And you'll see this kind of question on midterm, by the way, where we'll work with arrays. We'll have a base address. I think the homework has it too, right? Where it's like, oh, with like maze of A plus 14 or something like that. It's a pretty similar concept to that. Any other questions about that? Any questions are totally cool, guys. You want to talk about something with this? Totally happy to talk about it. All right, awesome. Let's go ahead and erase this real quick. Okay, so we can go on to part 2 now. So part 2 is a bit more complicated because we have to go ahead and assemble this. And we have a few assumptions first. First, let's assume that we have an accurate label map. So we have start defined, all these things defined right here. I'll just go ahead and erase this, and no one's confused. All right, cool. This looks good, right? All right, so let's go ahead and get rid of this too. If we want to assemble the first line, does anyone know how we go about assembling load word 015? Any ideas? Yeah, go ahead.
You have to figure out the options for those words.
Yep, exactly. So I'll go ahead and I'll pull this over real quick. All right, let's work on load word 015. So does anyone know the opcode for load word? 010, yeah, perfect. So does anyone know where the opcode goes in our 32 length bit string? Like what position is that at? 24 to 22, exactly. So what we can do here is, let's go ahead and worry about the semantics later. Let's just figure out how we're gonna actually construct this real quick. And this should be easier. Yeah, exactly. So what this means is that the bits 010 are gonna be at the position 24 to 22. Just like this. Does anyone know what's next after that? What do we have for positions 21 to 19?
Register A.
Yep, exactly. So in this case, I'll put 21 to 19, reg A. So do we put the value of reg 0 here or the number of the register? We do the number. So in this case, we're going to put 0, and we have 3 bits for 0, so it's going to be 0, 0, 0. Next, we have 18 to 16, and load word. This register right here is going to be our destination register. We're filling a value and putting it inside register 1. So in this case, we have 0, 0, 1. I'll call this dest reg. And then this is where the hard part comes in. The last 15 to 0 bits are going to be our offset. This is where the label comes in handy. We're going to go ahead and fill it, this entire offset field, with the value of the line the label's at. So over here, we know that 5 is that label, is that line 7 right here, right? So we can go ahead and put 7 in here, which is going to be, what's that? 4, 5, 6, 7, like this. And that's it. Did that process make sense to you guys, what we just did? Yeah, question?
And that's since it's 16-bit, that's 2 complement binary. Right?
Yep, exactly. So in this case, our first digit's 0, so it's going to be positive. But did that process make sense? What we did, we first found the opcode, reg A, destination register, and then our offset. The big question now is, how do we actually go about forming the string? Because we can easily get this information, right? But the question is, how do we go about transforming all of this into one string and outputting it as a decimal number? That's a pretty hard question to answer, but we can get through it pretty quickly. So first of all, in discussion, we talked about the bit shifting operator, mostly it's logical shift left, and what that does. What we do is, let's say we have, for example, 0, 1, 0. So I'll say int x equals 0, b, so binary, 0, 1, 0. If I go ahead and I do this in C, what's the result? Does anyone know? What is x now going to be? It's going to be 4 bits long. What's the value going to be? Does anyone know?
9.
9? Whatever 0, 1, 0, 0 is. So
Oh, yeah. That's right.
4. Yeah.
I thought we 101. by the
You're
way.
good. Yeah, yeah. So does that make sense what we're doing here? If you bit shift over by 1, you're adding an extra 0 here. So we have these 3 numbers right here, and I want to go ahead and move it to the opcode position. How many numbers should I shift it over by? 22, exactly. I go ahead and change this to a 22, like this. I now have positions 24 to 22 with the value 0, 1, 0 inside of it. And that's what we want, right? We want our opcode bits to be in positions 24 to 22. We have our opcode right here, shift over by 22, and now we have 0, 1, 0, bunch of zeros like that, right? Does anyone know how to combine binary numbers? Do you guys know what the bitwise OR operator does? You guys heard of it before? Anyone? Discussion? All right, cool. So what this does is, let's go ahead and assume we have I'll just call it RA for register A. In this case, it's going to be 0, 0, 0. So if I wanted this binary number 0, 0, 0, I know it's a bit redundant because it's already 0, right? If I want to go ahead and put these zeros in positions 21 to 19, what should my shift amount be? Anyone know? It's going to be 19. Essentially, it's going to be the last number here. Because think of it this way, right? How many zeros come after 19 or before 19? 19, right? I put a 19 right here, like this. I'll go ahead and get 0, 0, 0 with 19 zeros after before it, or sorry, 18 zeros before it. The way we can go ahead and combine it so that X and Y are now one string, we can use the bitwise OR operator. What this does essentially is, we'll go ahead and look at positions. Can you guys see this, by the way, or is this too low? We're good? All right. Let's go ahead and assume we have 0 and 0 in positions 24 to 22. We'll call this string X, and then we have string Y, which it's 0, 0, 0, and then we have 21 to 19, and that's going to be our register A value. If I go ahead and I say my result, let's call it X for now, right? I want to go ahead and take this field right here, these 3 zeros, and put it in positions 21 to 19. The way we can do that is say X equals X bitwise OR Y. What that does is we'll go ahead and figure out if there's a 1 here, we're going to copy it over to this string right here. And since this string is only for register A, what we're doing is we're only copying over the bits we set. And since register A is only 3 bits long, and we went ahead and moved its bits to positions 21 and 19, we're going to go ahead and copy all these bits over and put it here. So our result is going to be 0, 1, 0, 0, 0, 0. Does that idea make sense to you guys?
So while we are using the right arrow to move it a bit, I think we need to use left arrow to move the bit. You need to move the bit to left, so you need to use left arrow.
Oh, I use right arrows?
Yes.
Oh, my bad, sorry. It's hard working backwards. Thank you. There we go. Same idea though. Does that make sense to you guys? Sorry about that. All right, cool. So then we do the exact same process for destination register, and the exact same process for our offset. But our offset we don't have to do anything with because there's no shifting amount, right? We have a 16-bit number, and we'll go ahead and just bitwise OR that with our current bit string, and then that's gonna be our final answer for this. So for example, for this first line right here, our final answer would be all this right here. So by hand, that's all we have to do. And then we can go through every other example on here, but any questions about that process before we go into the other ones? Yeah, go ahead.
So you just did that to combine it all to one binary number?
Yep, exactly. And the cool thing is, if you ever print this out, which you have to print out to a file for the file reader, it'll automatically print out as decimal. So on the spec, we have it as decimal. So if you print out a binary number, it'll print out as a decimal number, which is pretty cool. That's all you have to do. Yeah, go ahead.
I don't know. I'm still kind of confused on the shifting. Can you explain that one more time?
Yeah, sure. So shifting. what we're doing here is basically, if we use a right shift, right? I was saying left shift the entire time, so that's my bad. Right shift goes ahead and it multiplies it by 2. What that means is we're actually, if we right shift by a value of 1, like this, let's say I have 0, 1 right here. This is my binary number right here, so I have 1. If I bit shift over by 1, what I'm doing here is I'm saying this number here is now going to become 0, 1, and I'll add 1, 0 right here, which is now 2. So I multiply it by 2. If I do it by 2 instead of 1, I add a second 0, and now I have 4. If I do 3, I have 8. The purpose behind this is I want to go ahead, and we know that our bit string for our assembly program, we need to have our opcode numbers in positions 24 to 22. So if I know my opcode for load word is 0, 1, 0, that 0, 1, 0 is good, but it's in the wrong position. That's in positions 2 to 0, right? If I set our opcode to be 0, 1, 0, I declare that, right? My opcode number is going to be 2. The issue with that is we want to have this 2, these 3 bits right here, in this position, but right now it's in this 2 to 0 position. I need to move it over so it's in that position. And you do that by using these bit shifting operators. Go ahead.
Instead of shifting over 22 one time, could you like in a sequence shift over 3 bitwise or the first register, shift over 3 bitwise or the second register, or would you not recommend it?
Oh, are you saying like a pipeline kind of where it's like you have 0, 1, 0,
Yeah,
and then you shift over by 3, then do that?
instead of just 22 at once.
You can do that, yeah. What you're
3.
saying essentially is what if, let me go back here. Yeah, let's say we have 0, 1, 0. What you're saying, correct me if I'm wrong, is well, if we go ahead and shift the row by 3, so we have 0, 1, 0, 0, 0, 0. We call this our opcode. We call this a register A. And then we shift over again by 3 to put register B in.
Yeah.
That works. That's totally cool. You can do that idea, or you can do the one I explained. They both are valid.
Okay.
At the end of the day, though, what you do want is to have your string format like this: opcode, reg A, des reg, offset. And this is unique to load word and store word. So go ahead and go over the other opcodes real quick, because if you understand this process, the other ones are pretty easy to understand. So this load word right here is almost the exact same process. The only difference is register 1 instead of register 0, and instead of having a label, we have a number. So our offset here is just going to be 3. That's all you have to do. For add right here, add's a bit different. Let me go ahead and. Does anyone have an eraser, by the way? Can I use my hand for this? Oh, hell yeah. Thank you.
I can give you a napkin.
That'd be pretty good too. Thanks. We got to buy one of those the other day, so a good old hand, I guess. What?
An old man.
I guess. Yeah. Also, it's perfect. All right, cool. So let's go ahead and do you guys want to cover the add instruction?
Yeah.
Cool, we can do that. So let's go ahead and work on add 1, 2. So quick question. Does this label here start impact anything that's instruction right here? It's on the same line as add. Would that impact our machine code at all?
No.
Nope, it shouldn't. So when we assemble, we only care about these lines, everything to the right of our labels. Whenever you assemble, as in translate a line of machine code, you never have to worry about is the label present on this line. The only reason you have to worry about a label is if you're referencing it over here in one of these arguments right here. So let's go ahead and work on add 1, 2, 1. So there we go. First of all, what's add's opcode? Does anyone know? Yep, all 0, nice. And that goes in what position?
24 to 22.
Cool. 1, that goes in what position?
21 to 19.
Yeah.
Yep, nice. And then 2, 0, 1, 0. That's 18 to 16. And then this is the one difference here. So this is our register A. So I'll put R sub A, R sub B, opcode. And then this last argument right here, this one's a bit different. Instead of going in 15 to 13, we're going to put it in 2 to 0. That's going to be 0, 0. This is going to be our destination register. So R sub B. So what we did here is we went ahead, found the number for this register right here. So 1, number for register 2 is 2. And then our destination register is going to go in positions 2 to 0. So 3 to 15 is going to be unused. It's all going to be zeros. So any questions about add? Yeah, go ahead.
In C, if you're trying to translate from an integer to a binary.
Oh, you can do, so you mean for shifting?
Well, I mean for like getting 2 to be 010.
Oh, so thing is your computer always thinks in binary, right?
Right.
So if you write decimal number, you can use bitwise operators, you can shift it and stuff. Your computer will implicitly think about it as a binary
But
number.
doesn't it think of it as a 16-bit?
It depends on your computer, but I believe so, yes.
Okay, so then when you do the OR thing, oh, I see what you're saying.
So you can-
because it's all gonna be zeros before the 010.
Yep, you could literally say, I'm gonna set my opcode for add to be equal to 0. My opcode for load word is gonna be 2. You can have it all in decimal, that's totally fine. It's probably more helpful in decimal sometimes. I use binary because that's like how you construct it and stuff. That makes more sense, but you can use decimal as well. But just know your computer automatically thinks in terms of binary under. So it's already like implicitly thinking about it that way. And then we can't have labels for add opcodes, by the way. So just know that. If you ever see a label for an add opcode, that's not allowed. You can't do that. Labels can only occur for load word, store word, and BEQ.
Send or we have to check for?
No, I don't think so. I'll get back to you on that, but I'm pretty sure you don't have to. You don't have to. I don't think so. I'll get back to you though, because I don't want to tell you the wrong answer.
No, I didn't.
Yeah, it's on the list, so you're fine. All right. BEQ, we can cover that one next too. So BEQ is. Sorry, any more questions about add? Yeah, go ahead.
Did you just say you could do it in decimal instead?
Sorry, what's that?
Wait, didn't you just say you could do it like in decimal or something?
Yeah, so you can write your register numbers in decimal. So I can write register B as a 2. Because your computer implicitly thinks in binary. So it's totally cool if I do like 2 with a right shift of 1. You can do stuff like that, yeah.
And then you would still order them?
Yeah, it's totally fine. Your computer, again, you can write in hex, you can write in binary, you can write in decimal. Your computer always thinks in terms of binary though. So it doesn't matter what you write it in because your computer will, everything under the hood is the same number, right? If I write 1, 0 or 2, like 0x2, sorry, 0b2. It's a B.
But you would still have to shift the decimal number to the right place before you order it,
Yes,
like the other decimal.
Yep.
Okay.
you still have to shift.
Yeah.
That's correct. Everyone good in that? All right, BEQ, this one is a little bit. Let's go over the first BEQ. 0, actually, there's a second one, because I laid a little bit. 0, 0, start. So the opcode for BEQ, I don't know what it is. Anyone know what it is? It's like 4, I think. 4?
Yeah.
1, 0, 0, right? That's going to be in position 24 to 22. Every opcode is always in this position, by the way. So you can have a function that does that, but just know for every opcode we have, for all opcodes, this position right here is always going to be for the opcode, 24 to 22. And then we have 21 to 18. This is going to be register A, which is going to be 0. We then have 21 to 19. 18 to 16, register B. It's going to be 0, 0, 0. And then we have our offset. This one's a bit different. This is probably the last tricky thing to describe. So the way this works is we need to figure out where start is on our label map. We know start is right here, but we're actually branching backwards. We have to branch with a negative number. The reason is that we are currently on line, what is this? Line 5, I think. 0, 1, 2. Line 4, right? And we want to go to line 2. So we actually have to branch backwards by an amount. And that's where discovering what start is, you have to do a few calculations. You first have to know what line you're at right now. So you can do is have a tracker or whenever you go through your while loop, whenever you're reading the file, and increment by 1. So you have line 0, 1, 2, 3, 4, line 4 right now. We know starts at line 2. We have to go back 2 spaces. And again, depending on your implementation, you might have to put a -3 here. I should know the answer to this, I don't. It's -2 or -3. I'm going to say -3 for now, but I'll look into this for a couple seconds. Just know you're branching backwards, and that should be your amount. You're branching backwards based on how far away its label is, and it's either -2 or -3. I'm blanking on it, so I'm sorry about that. But I'll make a Piazza post about it after this.
Wait, is that what you were talking about earlier, where it's -3 and then you add 1?
Yes, but I'm not sure if that's for the simulator or this. I believe it's for the simulator. I'll say -3 for now. I'll make a correction if I'm wrong on Piazza, okay? So for now, we'll assume -3. And that is because you go back 2 spaces, right? But our PC is always going to increment by 1. I believe the formula is actually in the spec. It should be like the line number minus PC plus 1, right? Is that correct? Can you verify that? It is perfect. So it's going to be -3 here. The reason why is because our line number for start is going to be 2. And then we're going to minus off our PC plus 1. So our PC right now is what line we're at right now. We're currently at line 4. Right here, this is line 4. We're going to subtract off 4 plus 1. So 2 minus 5, which is -3. We then put -3 right here. So does that process make sense to you guys? All right, good stuff.
So I'm looking at the spec right now, it might be equivalent, but PC plus 1 plus offset field is what it's saying.
We're talking about BQ.
Oh, B.
BQ, yeah. It should be like line number minus PC plus 1 or something like that.
Here.
BQ, branch the address PC1 plus offset field. Offset field.
Oh, excuse me.
Yeah.
Who's the instructor here?
Me?
When you have a minute, I need to ask a few questions.
Yeah, sure. We should be done here at.
Well, I kind of need it answered now.
Oh, I can talk to you now. Get back to
I'm sorry, guys.
Guess we're taking a break.
Yeah.
I see it.
Oh, it's not.
So what is it?
Office hours.
Okay. But how many students?
Are here.
Yeah.
Say like 25 probably. 20.
Is this, are you planning to make this a regular?
Like it's kind of larger than. No. Usually big one-on-one.
That's it. So usually something like that.
Yep. Yep.
Okay. And when does?
This is today.
Okay.
We have a varying schedule for class depending on my teacher.
Okay. So there are other sessions that are.
One-on-one, yeah.
Okay. You plan to use this.
Yeah. Is that okay?
Well, not normal.
Okay.
I'm gonna find out.
Thank you.
So what is your name?
Honestly. Yeah, sure. NMS. IMLS.
IMLS?
Yep.
Okay, and this is Luke's class?
Yep.
What
All right. And your office hours, your schedule, exactly.
4 to 5:30.
Okay, and how do I repeat?
Just my first name and as you were saying.
Yeah, that makes sense.
And
It's my first name, so nothing else, and as you were saying.
okay, all right.
Kind of weird.
You can stay today.
Okay.
I'll find out. You send email.
All right, thank you. Yeah, appreciate it.
Okay, thanks a lot.
Thank you. You're good. Yeah. All right, we can keep going, but we might be kicked out of Ugly Basement for future office hour session. So might have to do this remote in the future, so sorry about that. And in person's a lot more fun. We'll try to figure this out. Maybe the BBB, I'll figure it out, but we can stay here for today, which is pretty cool. Anyway, where were we? Oh yeah, Nuke and Halt. All right, so Nuke and Halt, I mentioned this before, but those things are pretty easy to work with. So all we have is an opcode. There's no arguments, right? Register A doesn't matter, reg B doesn't matter, guess reg doesn't matter. All we care about is the opcode, Halt or Nuke. That's it. So I believe Nuke is 6, right? So all we do is if we have the instruction for Nuke, we just go ahead and take the opcode for it, which again, I believe is 6. Anyone has that handy? 6, right?
It's 111.
Yeah, it's all.
7, okay.
Yeah.
Is Halt 6?
Yeah.
All right, cool. So for Nuke, we'd have something like 111, and then we'd shift it over by 22. And that's it. So when we say Nuke and Halt, they're going to be the exact same number regardless of where they are in the program. And by the way, you can only have 1 Halt. So actually, you can have more than 1 Halt, depending on how complex your program is. But for this class, we'll probably only have 1 Halt. You can have as many nukes as you want. Nukes are pretty helpful if you're coding an LC2K program. So for 1M, nukes basically are just like a way to make a new line without typing anything for separation of stuff. Yeah, go ahead.
Would multiple halts be if there were different paths or branches?
For branches, yep, you got it. Yep, exactly. So if I had like 1 branch, it'd be the 1 path, and then another branch, another path, that works as well. So yeah, you can have more than 1 halt, it's totally fine. All right, and then the fill statements, these ones are, again, for assembling, they're going to be just numbers. So if I have dot fill 5, what I should have is the number 5 in my machine code. I'm just taking this, and that's going to be the value we print out for machine code. I believe on the spec, let me pull that up real quick.
And then dot fill is the opcode in that case, or is it something else?
It just fills, so the opcode in this case is actually, it's weird. Dot fills are kind of like adds, so it's going to be a 0, 0, 0. All we're doing here is taking the value right here, and we're putting it, that's going to be our output. It's just going to be the number right here, the 5.
Yeah, no, that makes sense to me. What I don't understand is like code wise.
Oh, it's fill and opcode?
Well, yeah, because we check for the opcodes, right?
Yeah, so if your code is fill, which is sort of like it acts as an add. So you just check to see if the opcode is fill. You'd go ahead and that means you're at the end of your program. For this project, it's not enforced, but I recommend you guys do this. All of your .fill statement should be after your halt. So after all your opcodes like this, your .fill should be at the very bottom. And the reason for that is because remember our PC, the way it works is we go line by line. So you have .fill instructions in there. Your PC doesn't know how to interact with the .fill, but your assembler does.
So it's just in the test cases. it's like-
Yep. Yeah, exactly. So if you have like a .fill right here, that wouldn't be good. And once we do project 2, it's required that your .fills aren't between outcomes like that. Yep. And for this one, we would get -1. And start is, I believe, is that 2? Yeah, it's 2. Yep, perfect. What we're doing here is resolving where start defined. Starts defined line 2. go ahead, put a 2 right here. Yeah, question?
Can any label go with that field, or is it just like star?
Any label, doesn't matter what's named. It's totally fine. Yeah. All right, so that's it for the spec example. Do you guys want to talk about anything else in the project? Like test cases, maybe? Yeah, go ahead.
Quick question, these are stored in 591, these are stored in reg A.
Sorry, what's that?
Those are stored in reg A and values. So the
You mean like
5 and then like the target access goes.
how the algorithm is asking? You mean like is 5 inside register 1 right here?
Right, yeah, reverse.
Yeah, so in this case, we're loading 5. Actually, I can think about the program if you guys want to, and like what it's doing. That'd be helpful.
Yeah.
Sure. So let's go ahead and over here, I'm going to create a box. Register 0, register 1. If we use registers. All right. So I have register 0, register 1, register 2, register 3. We have up to register 7, but we're going to ignore that for now because our program only uses 0, 1, 2, and 3. So let's go ahead and first create a label map. So we know that start is on line 2. I'll go ahead and say 2, comma start. 5 is done, I believe. Yep. Okay, 6 is done, right? 3, 4, yep, 6. 7 is 5. 8 is -1. And 9 is ST error. So here's my first pass. I went through my assembly program and I figured out where each label is at. So again, we have start at line 2, done at line 6, 5 at line 7, -1 at line 8, and then ST adder at line 9. After that, what we'll do, and this is more of like a 1S thing, so it should hopefully help you guys think about project 1S once you guys finish 1A. Our PC is going to start at 0. PC means program counter. What line are we currently at? We always start at 0. What we first do is we see we have a load word instruction. Does anyone know how this instruction is going to be executed? What's our computer thinking? Anyone know? So what's happening here is we're going to load in a value into register 1. So this register right here is going to have its value changed to whatever value we branched through memory. So what does that mean exactly? Well, that means they first need to figure out where is our offset? What is it? Right now our offset is label 5. We know 5 is defined to be line 7. So we can think of this 5 as just being the number 7. Once I do that, we're going to go ahead and take the value inside register 0 and add it with 7 and go to that address. Our PC doesn't, but we are, for our memory, we're going to access memory address 7. So memory address 7 is 0, 1, 2, 3, 4, 5, 6, 7. We have this 5 right here. Now that we've accessed that, we're going to go ahead and put this inside register 1. It's going to be value 5. Register 0 is always going to be 0. So we have that done. Does that first line make sense to you guys, what we're doing? Awesome. No line 2 now. So we go ahead and increment PC. PC equals PC plus 1. PC is now right here. We have load word 1, 2, 3. So based on what we just did here, does anyone know what we're going to do for this instruction right here? So what are we going to branch to? What not branch, sorry. What memory address are we going to look at? Yeah.
Are you gonna load from 1 into 2?
Load from 1 into 2. What do you mean by that exactly?
From register 1 into register 2, the value from register 1.
So you're saying take value from register 1, put it in value of register 2?
Yeah.
So not exactly. Did you have an idea?
Is it, you take the value in register 1
Mhm.
and add it to, or
Yep.
you add 3 to it?
Yep,
and you put
exactly.
it in register 2?
Yeah, you take them. So exactly, you got it. So what we do here is we first want to go ahead and figure out what value is inside register 1. That's going to be a 5, right? So we want to go to line 5 plus 3, which is C shed, so awesome. 5 plus 3 is going to be 8. We're now going to look at line 8 in our memory, which is going to be right here. So -1. 5 plus 3 is 8. We go to line 8. There's a -1 right here. We're then going to go ahead and put -1 inside of our destination register. Does that make sense now?
Yeah, that makes a lot of sense.
All right.
Wait, I'm sorry, one more time. Where'd you get the 5 from?
Yeah, sure. Register 1's value. So
Oh,
register's
okay.
1 value is going to be 5 right here.
If
Let me
you,
go ahead. Yeah.
sorry, if you put like a 10 instead of the 3 there,
Yeah.
then we would exit with an error, right?
You would be out of bounds, so
Yeah.
you probably would just fill with 0 in that case.
Okay.
But your memory's uninitialized, so it's like basically accessing out of bounds in the right. It'd be that kind of error.
Okay.
Yep. So register 2 is now going to be -1. So now that we have that, we can go ahead and set our PC equal to add. So now what we're going to do is we're going to do add 1 to 1. Does anyone know what this does? For add 1 to 1? Yeah, go ahead.
Add the contents from 1 and 2 and load it that is 1.
Yep, exactly. So we know right here that R1 is 5 plus -1 is going to be 4. And we're then going to load that into 1. So 5 plus -1 is going to be 4. We go ahead and put a 4 right here. Perfect. We then go ahead and we break if register 1's value is equal to register 0's value. What this means is register 1 equal to 0? Which we can see it isn't. 4 is not equal to 0. So we're going to go to the next line. So PC is now going to be right here. What does this line right here mean? BEQ 00 start. What we're doing here is if 0, the value inside register 0 equals the value inside register 0, we're going to go ahead and set our PC equal to start. So since 0 is equal to 0, we're then going to go ahead and we're going to branch our PC back to start right here. Does that process make sense to you guys? All right, awesome. And we'll then repeat that exact same process over again. So notice how it's a loop here, right? We're going through this, and what's the way we exit the loop? We're going to keep on branching back to start unless we hit this line. What does this line right here mean?
Good value of register 0 equals the value of register 1.
Yeah, exactly. What can we interpret that as? Like in C code. Let's go ahead and say that it's like if register 1 is equal to 0. That's what that means essentially. If register 1 is equal to 0, if you ever see a BEQ with a 0, you can think of it as being a loop. What we're doing there is we're saying whenever our counter register 1 is equal to 0, we're done with the loop, right? So this is basically a for loop right here. At the end, we'll go ahead and translate this into C++ or C. Yeah, question?
Yeah. So the formula for BEQ says it branches to C plus 1 plus also.
Mhm.
What does the plus 1 mean again?
So +1 because what we're doing here is we would branch from start to right here, and then we do +1 to go to where we actually want to go. The +1 is there because whenever we finish executing an instruction, right, we're always going to increment our PC by 1.
Oh, okay.
Yep, and since we're right here, we want to branch backwards, we're going to go forward again once more.
Yeah. So you want it to leave what you want to leave the PC at its next instruction.
Yep, exactly. So we go ahead and account for the fact that we do PC +1 every time. That's why we have PC +1 there.
By the way, just broadly asking, are you talking about the first pass or the second pass right now?
Oh, this is more so explaining the program.
Oh, okay.
Yeah, did you just get here?
No, I just been zoning out trying to fix my S.
Sorry about that. I feel that. Oh, yeah, I talked to you last night, didn't I? Oh, yeah. You got it fixed yet, or is it still scuffed? Sorry, the Windows user. If anyone knows how to do Xcode stuff, hit him up. He's having a lot of issues, unfortunately. Xcode is just,
Or VS Code.
yeah.
Did you go over to add 1 to 1 yet?
It's not an.
Yeah, I haven't done that again yet, but I did it once. We'll do it again though. Yeah, sure. Yeah, we're gonna do the entire program, so don't worry. All right, so we did our first pass, guys, and we have register 1 is now gonna be 4. We're back here again, right? We're gonna add 1 to 1. So we're gonna add register 1 and register 2 and store that inside register 1. So 4 plus -1 is gonna be 3, right? We're gonna go ahead and do 3 here.
And this sort of thing happens in the simulating part of the puzzle.
Yeah, this is more simulator. Yep.
Okay.
I just want to cover both of them because they're pretty like intermixed.
Yeah.
0 is not equal to 1, or red 0 is not equal to red 1, so we're going to skip this. 0 is equal to 0, branch back to start, add 1 to 1. As you can see, all we're doing here is decrementing R1 each time.
Until equals like.
Yep, exactly. So that makes sense what we're doing here. Until it goes to 0, which it is right now. Once we do that, we'll be right here, PEQ 0, 1, 2. Anyone know what that means? So first of all, is register 0 equal to register 1 in this case?
Yeah.
Yep, it is. Cool. So we go ahead and branch forward PC plus 1 plus our offset. So our offset in this case is going to be +2. So go ahead and do 1, 2. We're at Nuke right now.
+1.
Plus 1. We're at halt. What does halt mean?
Means
We're
PC.
done. And that's it. So what this program basically looks like in C or C++ is, let's see, how can I do this?
You get to halt. So the 2 means that it's the offset field. So that's PC plus 1 plus whatever's in the offset field. So it's +2, right? Exactly.
Plus 2 plus 1.
Yeah, plus the program. In that case, would be on line 3. And it's the same as 3 plus 1.
So this is the program right here. All we're doing is looping from 5 to 0.
That's how.
And then we
that's how
exit.
the loop is, it goes.
It's a pretty boring program, but that's all we're doing.
Yeah.
So does this make sense to you guys? This is basically the C++ version or C version of all this stuff right here. All right, dope. Any other project questions? We still have like 30 minutes left, so talk about the projects some more. You can go to 1M too if you want. Yeah.
Talk about after the first pass, or if anybody first wants to talk about the first pass, then like.
Yeah, sure. We can do it both. So we can go over 1A again. First pass questions. Anyone who wants to go over first pass again? Anyone? You can raise your hand. Okay, 2 people. And then second pass. We can do both. So we'll go ahead and do first pass. Some more hands for that. So we can go back over here actually. So I've written down.
The first pass, second pass is part of 1A, right?
Yes. So what we just did with the registers, that's going to be 1S. 1S is, I'd say once you understand 1A, it's a lot less work than 1A is. 1S is a lot less work because you understand how this program works, right? 1A is pretty difficult to do. At first, this is why a lot of people are here, obviously. I was in the exact same shoes a couple months ago because assembly is hard to understand, right? Like translating this to C makes like no sense at first, but once you do practice with it, it becomes a lot easier. And the cool thing is they'll use the exact same ISA for the next 4 projects. So if you understand it now, you're golden for the next 3 projects. So yeah, for first pass, we can go over that again real quick. -1, thanks. Start. So what part of the first pass you want to go over? Just all of it, or?
Oh, I think I'm good on the first pass, but like I know other people already doing the first pass.
Oh yeah, so first pass people, what do you guys
I
want
just
to go
said that
over?
because then once you like jump to second pass, and that's what we do to them.
Right, I see. Yeah, go ahead.
Sorry, I have a quick question for the first pass. So
Yeah, sure.
with the X0 register, most of the people is 0.
Yep.
Do we dare do that, or do you have to like error check to see?
You don't have to error check it. Yeah, sure. So here's the thing. It's like if you personally write a program, you can change register 0. There's no like lock on it.
Okay.
But it's assumed that's going to be 0. So if it isn't 0 and then we give you a test case for that, like don't worry about it because well, it's like an error at that point, right?
Okay.
You don't have to error check for it. It's totally fine.
Okay.
Yep. And that's all for register values are only important for 1S. 1A register values don't matter. Does that make sense?
Yep.
Awesome. Got a question?
Okay, so I get that like first pass you go through and you get all the labels and like where their addresses are associated.
Mhm.
But for Phil specifically, like when is like 5 and -1 used? Like,
When are they used?
Yeah, like where are you coming from?
Yeah, sure. So let me go ahead and put this back real quick. This is 5, I believe. The reason why fills are important is because we want to go ahead and load a value into a register, right? For the simulator, it's not related, but this is why we have to do it. In the simulator, all of our register values are initialized to 0. So how do we ever get a value that isn't 0 inside a register? The way we do it is we have dot fills, and we can go ahead and manipulate numbers by using like ands and nors and stuff, right? So how do we get a number into a register? The way we do that is we have a fill statement, which is the number 5. If I go ahead and load in this memory address right here for 5, so again, 0 plus line address of 5 is 7. We go to line 7. We're going to go ahead and take this number 5 and put it inside register 1. That's for the simulator. For the assembler, all you're doing is figuring out what line 5 is on, which is 7, and that's your offset. So you see how we're doing 2 different things there? It's all one idea, but 2 different projects. Yeah, question?
Follow up on that. and
Yeah, sure.
Kind of asked on it earlier, but how are we gonna access that value 5?
Yeah, sure. How do we access it? Okay, good question. So we can walk through this step by step. So when we want to load a word into a register, we have to go ahead and first figure out what line address we're going to go to retrieve the memory. So in this case, what line is 5 on? Is it defined on the label? 7. Perfect. So for us to access a line number for load word, we first have to go ahead and figure out what the value inside register A is. So what's the value of register A? Yep, exactly. Because 0 is always going to be 0. 0 plus our offset is, yep. We go to line 7, which is right here. And then for our machine code, right? So this is all for the simulator. So for the assembler, again, all you have to worry about is changes 5 to 7, you're done. For the simulator, you're given machine code, right? You're given machine code, and all you can see right here on line 7 is just number 5. You would then go ahead and take the 5, because it's on line 7, and you would put it inside register 1. Does that make more sense? Yeah. Awesome. We can go ahead and go through this example too. Register 1's value is going to be 5, right? 5 plus 3 is 8. We go to line 8, which is -1, take this value right here and put it inside register 2. Does that make sense? Taking the value of reg A plus our offset, go to that line, get the value, put it in our destination register. Awesome. Any other first pass questions you guys have?
So for load word and store word, would it be like the same thing?
Yep, exactly. So store word, what you're doing is you're storing a word in memory. So I went ahead and I said store word 017. So let's go ahead and just for this case, let's assume the value of register 1 is going to be, we'll say like 12. For store word, what's happening here is I'm going to go ahead and go to memory address 7 because reg 0's value 0 plus 7 is 7. I go to line 7 and I overwrite this 5 with a 12 right here. Again, we're assuming that register 1's value is going to be 12 here. That's the number I just made up.
Oh,
We'd go ahead and put a 12 in right here. That's how store word works. And then let's say I did load word like this 027. I then go to 7 plus value at 0, which is 0. Go to line 7, take this value right here, which is 12, and go ahead and put it inside register 2. So you can see how you can basically manipulate numbers, right? Let's say I went ahead and added like 1 to 12, so I got 13. I can then go ahead and put that back inside memory and access it later. That's why load word is already useful. And in project 1M, that's like most of the project is how do I like manipulate numbers and then store them in memory somewhere so I can use it later? Yeah, question?
So you said that when we print it to the file, it's gonna switch it to decimal for us. And I was just confused about with the negative numbers and 2's complement, how that would work. Because if it's storing as a, a 16-bit, but all of our answers are supposed to be 32-bit.
Yeah, so your negative numbers is totally fine, right? So just running them at 16 bits, that means our offset field is gonna be 16 bits long, right? So if you have like -15, right? Let's say that's your offset, for example, you can use bitwise or that with your, let's say this, right? Store word 01 offset. Let's say your offset is a negative number. Let's say in this case, like -12. if you go ahead and you process this, so you know the store word opcode is this, red 0 is this, which one's this, and you format your entire string.
Mhm.
If you take that, you bitwise or that -12, your answer is going to be right.
Okay, but then when we print line 8 though, the machine code for that is supposed to come out as -1.
Yep.
But if that's I guess more what I meant.
So let me ask you this. What is -1 and 2's complement 16-bit? It's going to be some number, right?
The 1 and 1 on that.
Yes, you get a bunch of ones, then like a 0, right? So what's it in 32-bit? It doesn't matter, right? It's still going to be -1 at the end of the day. So that's totally fine if it's in 2's complement, because if you output -1 in 16-bit or 32-bit, it's still the same number, right? Sure, it looks different, but when you output it as decimal, it's going to be the exact same thing.
Okay.
So it shouldn't be a concern. Yeah. Does that answer your question though, sorry? Your question good?
Yeah.
Awesome. Yeah. You're good?
Yeah, I think so.
All right, awesome. You think so? Or we can go over it again if you want.
I'll go home, type it out, and then I'll see.
Maybe you
I'll
can
know if
go
I'm
over
good.
his question again.
Oh yeah, sure. Okay, his question?
Yeah.
Go to yours real quick. Yeah.
I think the situation is like, if it's 32 bits and your value is like 3 and 1.
Yeah.
Or it's a different number, you can just end up with like 32 bits of all. It's kind of like covering it up.
That's a good point. So we can talk about this thing called Bitmask real quick. I'm gonna erase this. Let's go ahead and check something in the projects back real quick before I get back to you on that. Okay. Yeah, sure. Give me 1 second. I'm just gonna check something real quick. Yeah, thank you. I just want to check one thing before I give information about it. Yeah. I just figure out what the two has. All right, so first, to go ahead and answer your question, I'll go back to your question with the confusion. So your question again was the -12 thing,
Yeah.
and what about it again?
I'm saying, just can you run through like what happens when you have the -12?
Yeah, sure. Bad example of store word. Okay, let's assume, for example, let's go BEQ, because obviously store word, you can't have a negative number. You can have a negative number here, but in this case, we're branching to memory address -12, which makes no sense, right?
Yeah.
So let's look at BEQ. Let's say, for example, I have a -1 right here. And then your question was, how do we resolve this essentially?
Yeah.
Like for assembling it?
I guess because I was just confused why you could put -12 there, like for the store word. Because I'm like,
Oh no, I was saying that you. Okay, I see your confusion. You mean for this example where I'm storing a number in? Okay. So let's go ahead and let's go back to our original program. This, and then we had a 5 right here, I believe, right?
I think so. Yes.
Yep. So let's go ahead and assume that we start our program off, we do some stuff, and we go to this part of the code, and register 1 value is going to be 12. What I'm saying here is the way store word works is we're going to go ahead and overwrite the value in memory. So we first go ahead and figure out what line it's 5 at. It's at 7. I think this is 3 before. Okay. So
Yeah,
5 becomes 7, right? We then do value of register 0 plus 7. We go to line 7, which is 5. We then go ahead and put the value of register 1 at this memory location. So since 5, we're going to change it to a 12. So does that answer your question?
Yeah. Okay.
All right, awesome. And then your question, if we have a 32-bit 2's complement number, but we have 16 bits for it, how do we work around that? Is that your question?
I mean, I understand it now. If it's just, if we just have it saved as int with the 0B thing, that'll just assume it's in 2's complement, right?
Your computer automatically thinks 2's complement.
Yeah,
So
yes, I think I got it now.
Oh, Okay, I'll explain one other thing you can use called Bitmask. So you guys remember what Bitmask do in discussion? Probably not. Okay.
It's like the and, right?
Yep, exactly. So let's say we have 0, 0, 0, 0, f, 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 f. Let's say 0x. Okay. So this is called a bitmask. So remember how we converted from hexadecimal to binary or binary to hex? We can group one hex digit like this into 4 different binary numbers, right? So what is f in binary? It's 1, 1, 1, 1. What is ff in binary? Like this. We have these groups of 4 right here. 4f's looks like this. This is 16 bits, right? We can think of this. It's 15 to 0. If we have an offset, right? We can always just go ahead and use the and operator like this, bitwise and let's say our offset is like some number, right? And it'll compare 1 against that position, and then there's a 1 in both of them, it'll produce a 1. That's how a bitmask works, and that's kind of related to what you're asking. So I just wanted to explain that because it is useful in project 1S, but we have to go ahead and extract bits from strings. So I just want to make sure you guys are aware about this. I think it's a cool concept though you'll be using the project. And this is more towards 1S though, because in 1S you're given machine code and you have to go ahead and extract information about it. Yeah, question?
So that means you're saying like the offset field, if you have it only configured 16 bits or something.
Yep.
The issue is like 32 bits.
Yeah, and they said use a bitmask.
Yeah.
Yeah, that's totally cool. You can do that too. That's why I have this right here, right? Because f is 16 bits, right? And our offset is 16 bits long. So if you apply a bitmask like this, it'll make it into a 16-bit fuse complement number.
You have to check to make sure that it's too large.
Yeah, if the offset field is too big, then you just go ahead and you say error, like number's too big.
But if it can be represented by 16 bits.
Yep, exactly. I believe the number is like 32,000, I think. Yeah, 32,767 to negative 32,768. If it's in that range, you're fine. That question?
When you said disco error and then print that out, did you actually mean print that out or exit error?
You exit, so an error means you exit 1.
Exit one.
Yep, exit 1 means you have an error. Exit 0 means everything's fine. All you do is exit 1. You can print an error if you want debugging, but it's not necessary. Yeah, question?
What point in the program would you recommend checking for that?
For the errors?
No, just for that specific error.
Yeah, offset right here for store word, load word, and BEQ. Those are the only 3 opcodes that have offsets with them. So if your offset is bigger than the 32,000 figure, then you go ahead and you exit 1.
But it will do nothing. Well, the program automatically give us an exit one.
Well, automatically?
Yes.
No, it won't, because you're assembling it, right?
Yeah.
So you have to dictate, is the file able to assemble or not?
Okay.
Does that make sense? Because your program doesn't understand that your offset field is 60 to 0. If you check for that manually and you figure out, oh, the 16th bit is a 1, that means it must be bigger than 2 to the 15, right? That's an issue. Then you exit 1. Your program implicitly doesn't know that, oh, anything bigger than 2 to the 15 is bad. You need to go ahead and check whenever you have an offset. If my offset's less than this or it's bigger than this, that means that I have an issue. I'm going to exit 1.
So actually, my question is that if on the first track, if we met some stuff which is not labeled, so that it is not initialized or it is not defined. So,
Oh, you mean a label?
Yes. So it will just the program automatically could give us an exit.
Oh, so you're saying on the first pass?
Yes.
So on the first pass, you shouldn't have to worry about anything like that for the offset amounts. So checking for offset amounts, I believe, is a 3rd area to check for. And that should all be done in the second pass. In the second pass, it's going ahead and checking your offset and load word, store word, and BEQ. So in this example right here, so we have, let's put this back to how it was before. It was 5. Let's say this is at line 0, and there's a bunch of code in between these files, right? Or in between these lines. And 5 is actually at line like 50,000, right? We can't branch that far down because our offset can only be 32,600 something, right? So in that case, you check the offset amount. If it's too big, we go ahead and exit one. So you're checking that inside your second pass. Your first pass, all you're concerned about is, hey, where's this label at? Where is start defined at? Where's done defined at? And that's it. So the big idea here, guys, is in the first pass, all you're checking for is where is label defined and are there duplicate labels? Yeah, question?
To check for duplicate labels, is that gonna have to be like another for loop, you think?
Yeah, so whenever my like suggestion for that is go ahead and create a label map. So again, have that 2D char array. And then from that, you can go ahead and iterate through it before you put a label in. So let's say I encounter start. I'd first go ahead and check to see is start already in my array. If it is in the array, that's gonna be an issue, right? That means you already defined it. If you didn't define it, put it in there and keep on going through your way. Yeah, question?
But if we have two starts like on the offset side, that's fine.
Yeah, definitely, right? You can reference it as many times as you want on the right-hand side. It's sort of is an analogy, might not work, so I apologize for this, but for those math people out there, you can think of it like a function, right? Where it's you can map, so an x can map to a y, right? Let's say we have a function where it's like f of x equals 2. And then this is true for x equal to 2, 4, 6, 8, 10, 12, etc., right? That's sort of like these x's in the function, right, are mapping to the same y. That's totally fine though, right? What you can't have is two labels where it goes, oh, 5 actually maps to here and it also maps to here and here. You can't have that, right? So this is actually just, it's literally a mapping, right? These are like the x's, these are the y values. These labels can map to only one line in our assembly file, but this value right here can map to as many offset fields as you want. So for duplicates, you're checking to see on the left-hand side, does it equal more than once? And the right-hand side, you're checking to see, does 5 actually exist? That make sense? Yeah, question?
Are you still talking about class first class or
I mean, kind of. We can talk about it if you want to.
can I ask a question somewhat about the second class?
Yeah, sure.
Walkthrough slides.
Oh, yeah, go for it.
In
I haven't seen them yet for reference, so.
in the first slide it says in second class, when you encounter a label, go to where it's going to be and insert the correct value. Put it into
For a second pass,
yeah.
you're saying insert the correct. Oh, what they mean probably is we encounter 5, right? We search label map, we figure out that 5 is on line 7. Go ahead and insert 7 into our offset field.
Oh, into the offset.
Yes. It's called resolving the symbolic address. Because 5 doesn't mean anything, right? But 5 is defined down here.
So that could just be like another loop for your story.
Yeah, exactly. So whenever, yeah, you got it. Whenever you encounter a label like this, we branch off into some for loop, search our label container, and we figure out where 5 is defined. Yep. Yeah, great question. I guess we can talk about process too if you guys want to. So hopefully this stuff is all clear to you guys. We can talk about code design now. So anyone, if you got any concepts, like how would I code this in? Yeah. To a machine code file. So yeah, print to a file, yeah. And if you want to debug it, you can just do printf as well. Because we don't grade your terminal output, but we grade the file output. So I did for all the projects, you guys can do this too, is you can also just print to your terminal for debugging purposes. That's pretty helpful. And then we only grade you based on what you print to the file. Yeah, exactly. At the end of it, you can have like what I recommend is you have an array of integers, right? Because you're storing these instructions which are integers. At the very end, go ahead and print out the entirety of your array. Yeah, you can do that. Yeah, or you can print to the file line by line. Yeah, go ahead.
So if I'm looking at this left here, what values are going to be in spaces where they're on pages?
Oh, what's going to be like here and here?
Right, exactly.
You can have an empty string.
Okay. How would I declare that?
You can just do the array.
Like if I was declaring the array, how could I like declare with a bunch of null values?
What you can do is if label is equal to null, like it doesn't exist, you can go ahead and do a string copy, strcpy, of like this empty thing and then your label. For the array, so it'd be like array of like I. And that way, you know nothing's there, right?
Right.
So whenever you do string compare eventually, so you have all these labels and stuff initialized, right? Now let's say, for example, you get to start, you see at start isn't empty. You go ahead and just copy start to this right here. And then you can loop through it eventually and have like string compare of your array index I and then your label. And the weird thing about string compare, by the way, is it'll return 0 if they're equal, not 1. So if you want to figure out if they're equal, do equal 0 or negate it.
So this first thing you said that you have to check if it's empty, why would you do string copy and not string compare?
Oh, I'm saying like if you know it's empty, then you can copy over an empty string to it.
Oh, okay.
But I think it defaults to being empty, so I might just be redundant. But you first want to determine like what your label is. Does it exist? Is it empty? If it's not empty, you can go ahead and copy over that way.
But you did say that like an array is initialized and empty values.
I believe it is. I can't, don't quote me on it though.
Okay.
I'm pretty sure it is though. Yeah, just double check it.
Yeah.
And even if it isn't, it's a pretty easy fix, so it's not like a big break thing. Does anyone know actually? Are 2D char arrays initialized to the empty string? I imagine so, right? I'd assume so, but they are? Yeah, cool. And cool. We got 2 maybes, so that's probably a yes then. All right, what else? Anything? Community code with related questions for 1S, 1A, 1M. All right, how much time do we have? Oh, right on time. All right, cool. So thanks everyone, guys. Appreciate it. If you have any questions, I'll stick around for like 5 more minutes or so. Yeah, discussions tomorrow for most of you guys. I think some people had it on Wednesday, but I think the project's due, is it next week?
It's due next Wednesday to talk.
Yeah, cool. So you have a couple.
Thursday.
Yeah, you've got about time then. Yeah, go ahead. Yeah, sure. Yeah, of course. So let me stop the recording. Sorry.